Hello, we are the Island City Explorers from Winona State University, and this is our final video. Today we're going to review our walkthrough and fly-off experiences and discuss our results, map of our mystery area, and lessons we have learned during this project.
The team members will introduce themselves from left to right. Hi, I'm Maureen Pellicero.
I'm Stephen Shaw.
I'm Nahum Namara.
And I am Serdar Çiftçi. To begin, I am going to talk a little bit about our walkthrough. So we were able to identify one of the packets as magnetic, but we weren't able to identify what the other packets contain. For mapping, we recorded both horizontal and vertical perspective of the walkthrough course. We did collect granular and fluid samples during walkthrough. Between our walkthrough and fly-off, we were able to improve team operations such as battery replacements.
Now we will move on to discussing how our fly-off went and providing the results we obtained. Overall, our fly-off went okay, but could have been better. Our camera gantry and sensor suite both worked, but we ran into issues during flight. Our drone controls became inverted for unknown reasons, and our drone had difficulty gaining altitude while flying both the mapping and sensor configurations. The best part of our fly-off was sample collection. We were able to gain more than 1 cc of both fluid and granular samples. We also got enough in-flight video to put together a basic map of the exploration area.
In the week before the fly-off, our RF link, which communicated with the servo motor to tilt the camera, stopped working. We decided to fly with the camera in 2 positions on fly-off day, manually changing the perspective. We began with the camera pointed downward and took video of the course. The app lagged, but the video saved to the SD card. We landed the drone and changed the perspective of the camera to forward-facing. We had difficulty reconnecting the camera with the app, so unfortunately none of the video from our second perspective was saved. We had planned to use data from the ultrasonic sensor for feature height, but due to turbulent conditions on flight day, we were unable to gather meaningful information. Also, the lasers we attached to the camera were too close together to make the scaling, which made the scaling difficult to determine from a high perspective. We were able to use screenshots from the first perspective to create a map. By measuring the distances between features, we created this 3D map of the course using Tinkercad. While we are not able to determine specific dimensions, we are confident the proportions of this map are accurate.
Here we observe the blinking light on a bucket located at the top of the towers. Here is a picture of our course taken by the drone at high altitude.
Here are 2 pictures that will show the sand pile in the course that we collected a sample from. As you can see, it looks like it's a pile that's on maybe a baking sheet, and it kind of looks like there's some black regions on the top of it, which were pretty interesting.
In this picture, as you can see, there's a water bucket with some brownish dirt on it.
These next 2 shots are of an image we viewed on the ground of the course. We believe they are possibly images from another planet, maybe Mars.
This next shot taken from the drone shows an image that we observed on the front of the stack of bins. We're also thinking this might be a picture of possibly Martian terrain. We went through a number of changes during the design and test process of our sensor suites. At first, we were going to try to send all of the data collected over the RF link, including the ambient data in real time. We weren't able to get this to work, but we were able to send 2 floats, so we simplified the design and sent only the magnetic and thermal camera data in real time. This was more reliable and simple. We also ended up changing from a thermistor to a no-contact thermal camera because of difficulty in actually getting the thermistor to make contact with objects in flight. Here are pictures of our graphs of data collected during our fly-off. Our course exhibited an ambient pressure of around 100.26 kilopascals, ambient temperature of around 21.8 degrees Celsius, humidity of around 20%. Here are the graphs from our probing sensors. We observed a magnetic field of around 100 microtesla with a spike from team calibration at the beginning, a temperature of again around 21 degrees Celsius, and flew within 1 meter of the ground. We were able to probe only the frontmost package in the course due to difficulty in flying the drone, included inverting controls and difficulty in lift. This probing happened around the 1.9 minute mark in our data. We believe this first package was neither a magnet nor a hot or cold object.
And here we have a time-lapse of our spy cam pictures.
These are the sample collectors we used on our third configuration. The one on the left is the one we used for liquid sample collection, and the one on the right is the one we used for granular sample collection. You can see there's coins attached to it. We did that to have a tilt so we can collect more samples. The one on the back is the frame we used to attach it to the drone.
Here are the two videos that we collected samples. First one is granular samples, as you can see in the video, and the second one we tried to collect fluid sample.
This is the sample of the fluid we collected, and we got about 2.4 milliliters. We think this sample is just water. It has a pH of around 7, and from our observations it's not clear, it's a little dirty.
For the granular sample, we collected 1 cc of the sample, and we think that it is some sort of sand, partly ferrous. As you can see in the video, we did the test using magnet to find out if the sample is ferrous or not, and it concludes that sample is ferrous.
For each sample that we collected, we measured the density of the fluid and the granular. So for the fluid, we got about 1.05 grams per milliliter plus or minus 0.1, and for the granular, we got about 1.57 grams per milliliter plus or minus 0.04.
As a team, we have learned a lot from this experience. We had originally laid out a timeline over holiday break to finish out the project. This timeline called for completion of all the electronics and mechanical components by March 1st.
We ended up continuing to troubleshoot and change components through March, making it hard to get any good flight practice before our fly-off. Even in the morning of our fly-off, we ended up hot gluing and soldering lasers to our camera gantry as a last-minute change after the RF link in the flight tilt was cancelled.
We no longer had the need for a teensy, RF link, or soldered breadboard, and were able to add back the lasers that had been cut due to weight constraints. We did practice flying, especially with the sample collection devices, but recognized that flight practice might have led to better outcomes in data collection and overall fly-off performance.
Also, we had difficulty charging the batteries and realized the light glowed red when plugging in the charger with a battery already connected, and green when connecting the battery after plugging in the charger. So it is possible we tried flying with batteries that were not fully charged during the fly-off. In summary, the walkthrough was very helpful in refining team operations for the actual fly-off. We faced challenges flying on fly-off day. We gathered footage from the bird's eye view and were able to create a 3D map of the mystery course. We gathered ambient data using our sensor suite, but were unable to probe any objects of interest except for the first envelope. We created graphs of all sensor data. We were able to collect both granular and fluid samples and analyze these further. We hypothesized the granular substance to be sand containing magnetic elements, and the fluid to be water with contaminants resembling seaweed.